Hello, and welcome to our second to last PowerPoint module for this semester. We're going to be talking about inferential statistics. And inferential statistics can be a bit tricky, so we're definitely going to spend time talking about this in class as well. All right, but really our discussion of bivariate and multivariate statistics has culminated to this point, talking about inferential statistics. Our objectives for this week are to first introduce inferential statistics and the process of hypothesis testing, and then we're going to also define statistical significance and do examples of this. I expect this module will take about an hour. It might take a little bit more time because I do have more slides than usual, because I really do want to explain this well for you so we're prepared to discuss in class. Here are your deliverables for this week. As usual, you have your PowerPoint module, this module, due Tuesday night by 11:59 p.m. There are 3 questions for you to respond to, and you have no assignments due this Friday. All right, so it's just the module and, of course, coming to class. Which leads me to this very important reminder, we do not have class this Wednesday. This Wednesday is your last spring break day. So we're not going to meet on Wednesday this week. We are going to meet on Friday. We also have a few more changes to upcoming assignments, and I have updated the syllabus and posted that on Inquire for you. First, I'm pushing the due date for your full research proposal assignment. It's now due on Friday, May 14th by 11:59 p.m. This is the last day of class, right? So it's due on the last day of class by 11:59 p.m. on Inquire, as usual. Related to this, we are not going to be doing final presentations. I want to give you more time to work on the proposals, and I recognize that this is a very busy time in a very unusual semester. So instead of doing final presentations during the last week of class, you're going to write a 1-page reflection paper on what you learned in this course and how you might apply what you learned outside of class. Okay? And these reflection papers are going to be graded based on completion. Instead of the final presentations, this is what you're going to do for those 20 points. And then finally, given that we have moved our entire class to Zoom only for the time being, your final exam is going to be a take-home exam instead of an in-class or timed exam during the final exam period. Now, your final does still need to be turned in by the end of our final exam period, which is on Thursday the 20th at 5 p.m. Okay, so you're going to have a take-home exam. Just like with your midterm exams, you're going to have several days to complete it, but you do need to turn it in on the 20th by 5 p.m. So those are the 3 big changes coming up that have been reflected in the syllabus. The reason we're doing this is to give you more time to focus on that research proposal assignment and to really give you a little bit less to do for the last few weeks of class. I want you to focus on the proposal assignment, and I also want you to be able to manage your time for this course and other courses. Okay, so these are the major changes that we're making for the remainder of the semester. One last bit of housekeeping before we get to our topic for this week. You do still have that final research proposal due. Now it's due on the 14th, so it's a little bit later, but I did want to go through the different components of the proposal that you have already done and you already have drafts of and what you still need to complete. Okay? And also a side note, I have returned the literature reviews. For anybody who turned those in, you have a returned literature review on Inquire. I am still working on the research designs, but here's what you should have completed at this point and what you still need to do for the final proposal. At this point, you should have a literature review draft. I was missing a few, so if you don't have a literature review draft, then you do really need to get moving on that, okay? So you should have that completed. You should have a research design draft as well, and this includes hypotheses, research methods, sampling procedure, instruments, ethics, those appendix items, which really are your research instruments. This should already be done, and you should be using these, obviously, for your final proposal as well. So here are the major components of the final proposal, including what you've already done. You need a title page, okay? Easy points. You need an introduction, okay? And the specifics for each part of the final research proposal are in the prompt for the proposal. So go back to that prompt for the full research proposal assignment. It is on Inquire. I believe I also handed it out in class for those who are in class. So you need an introduction. You also need to make any necessary revisions to your literature review and research design based on the feedback that you've already gotten or that you will get. In addition, there's one last section of the research design that wasn't included in that research design assignment that you've already done. I want you to add a section on your method of data analysis. Okay, so this is the last section of the research design, and you should say what univariate, bivariate, or multivariate analyses you're going to do for your proposed research. Then you should have a conclusion. Again, information about what should be included in your conclusion is on the assignment prompt. After your conclusion, you should have all of your references organized from all sections of your proposal. They should be alphabetized. And then make any necessary revisions to your appendix items as well, those research instruments, whether that be an informed consent form, self-administered questionnaire, etc. Okay? These are the components that you should have in your final proposal. Start thinking about this now, even though it isn't due for a few weeks. Let's get into our topic for today, and as usual, we're going to start with an opening question. Here's your question. In hypothesis testing, what is the null hypothesis? What is the null hypothesis in your proposed research? And if you do have multiple hypotheses in your research proposal, you can just state one null hypothesis. Okay? So pause the PowerPoint module here and answer that opening question on Inquire. Now let's get into our topic for this week. I want to briefly review a couple of things from earlier in the semester so you can draw connections between what we're discussing today and what we've discussed really at the very start of this course. Recall that quantitative social research applies deductive reasoning. This means we're developing hypotheses or a hypothesis based on theory, and then we're testing that hypothesis to see whether the results of our statistical analyses support our hypothesis or not, right? This is really the crux of inferential statistics, which is what we're going to discuss this week. There are also types of statistical analyses that we use to test our hypotheses, whether those be univariate, bivariate, or multivariate. So this is the necessary foundation to then get into hypothesis testing and inferential statistics, remembering that we're applying deductive reasoning here. All right, let's talk about inferential statistics. And we're going to start by talking about inferential statistics more conceptually, so not really getting into the statistical nitty-gritty of it. We draw inferences all the time in our day-to-day lives. And inferential statistics is a way of drawing inferences from the information, the statistics that we have. Let's break down what we mean by inferring or inference. To infer something means that we're drawing a logical conclusion based on the information that is available to us. And like I said, we draw inferences all the time in our day-to-day lives. For example, if I get a stomach ache after eating a whole chocolate cake, and this happens repeatedly, then I could probably draw the inference that it's the chocolate cake that's doing it, right? And that there is this relationship between eating chocolate cake and getting a stomach ache, okay? Now, let's relate this to quantitative research. We use statistics in order to infer whether the correlations that we find in our sample, so remember, say relationships between two variables, we use statistics to infer whether these correlations are true for the population from which our sample was selected. To say this differently, we are determining how confident we are that our findings can be generalized to the population from which our sample was selected. Okay? This is what inferential statistics is all about. I do want to say there's one big caveat here. Inferential statistics is not a way of testing sampling error. That is, we're not testing whether we drew a random sample from our population. We can have a random sample and still happen to get a sample that is not representative of our population. Okay? So this is different from, we've talked about generalization in this class, whether our results can be generalized. Now we can think about this in a couple of ways. We can think about whether our sample generalizes or reflects our population. Here we're talking about whether our findings from a random sample can be generalized to our population. And we'll continue to make that distinction throughout the module and in class as well. Okay? This is really the crux of inferential statistics. Let's do an example to try to get a better understanding of inferential statistics. Okay, so that's what we're going to do here, except we're not using a social science example just yet. Here we're using the example of M&Ms. Let's say that you dump 1,000 M&Ms in a paper bag without looking at them, so you don't know what they look like, and then you randomly draw 10 M&Ms out of that bag, which is akin to a simple random sampling. It's not a very big sample, so probably not the best idea to just draw 10 and draw a conclusion from that, but that's beside the point. Let's say you're drawing 10 M&Ms out of that bag. If this is a standard bag of M&Ms, then you would expect to get a variety of colors, right? Maybe a couple of blue, a couple of green, brown, and so on, if it were a standard bag. So now let's ask the question, what is the probability of drawing 10 blue M&Ms if we have a standard bag? I did a little bit of background research for this example, and it turns out that nearly 25% of M&Ms in a standard bag are blue. Okay, even though there are multiple colors here, blue M&Ms are overrepresented just a little bit in our bag of M&Ms. People must like blue. So now we can calculate the probability of drawing 10 blue M&Ms in a standard bag, because we know that about 25% of the time we would be expected to draw a blue M&M in a standard bag. So I can calculate this, the probability of drawing 10 blue M&Ms, by multiplying the probability of drawing a blue M&M 10 times. So the probability for each time it's 25%, so it's 0.25. And then we multiply 0.25 by 0.25 by 0.25 10 times, and we get our probability. And it's a very small value. It's 0.00000095. This means that the probability of drawing 10 blue M&Ms from a standard bag is very small. So if this were to happen, we actually did draw 10 blue M&Ms in a row, we might infer that we actually have a bag of all or mostly blue M&Ms, right? Because the probability of actually drawing 10 blue M&Ms is very small in a standard bag. It is still possible that we drew a fluke sample of 10 blue M&Ms from a standard bag, but it is very unlikely, okay? I'm going to start to apply some of the language of hypothesis testing here, okay, to this example. Our initial hypothesis going into this is that if we're drawing from a standard bag, we're going to draw a blue M&M 25% of the time with each draw. But after drawing 10 blue M&Ms in a row, we're probably going to reject that initial hypothesis, right? Because it's very unlikely that we actually have a standard bag here. Right? So that's starting to apply that language of hypothesis testing. We're going to come back to this example. I think it's a useful example for understanding probability in inferential statistics. Of course, it's not a social science example, but I think sometimes Candy can help us to understand things, right? Here's another example. This is an actual social science example using the General Social Survey, and one that we've actually used before in our PowerPoint modules. So let's say we're looking at generational differences in attitudes toward marijuana legalization. In looking at the table below, it looks like there are substantial generational differences in attitudes toward the legalization of marijuana, right? So if we look at our table, we see that for Gen Z, our youngest generation here, ages 18 to 20, 70% say it should be legal, 30% say not legal. And then if we go to the opposite end, at the silent generation that are age 71 and over, we see kind of the reverse, where 37% say it should be legal and 62.9% say it should not be legal. Now, in just eyeballing it, it looks like we have some difference here, right? It looks like we do. But how do we assess whether we can generalize this difference that we observe to our population? And let me actually, and I'll quote the slide here, we're going to put this in terms of inferential statistics. Can we infer that the observed generational differences in attitudes toward legalization of marijuana actually generalize to the US population, which is our target population in the GSS? So this is an example, again, that is more directly linked to social science, going beyond M&Ms. We're taking a look at the probability that the relationship we're seeing here between generation and marijuana attitudes is true for our population. Now, it's possible that the sample drawn by the GSS, even though it was random sampling, is a fluke sample. Maybe they happened to get a sample of people from the silent generation who have attitudes that don't reflect the population within that generation. And perhaps in our actual population, the probability of saying that marijuana should be made legal is the same for each generation. Maybe there really isn't a difference in our population. And just like in the M&M example, where it is possible that you happen to draw 10 blue M&Ms in a row from a standard bag, this probability is very low. So we infer that the finding of all blue M&Ms generalized to our M&Ms population. All right, so if we put this in another way for the M&Ms example, if we assume that we have a standard bag of M&Ms, the probability of drawing 10 blue M&Ms, can this be generalized to our M&Ms population? Now here, we're saying, okay, well, we have these findings that seem to suggest that there are some generational differences in attitudes toward marijuana legalization. What is the probability that what we're finding here is some real association in our population? Okay? And this is what inferential statistics can tell us. And at this point, I'm not telling you how statistically we would do this. That's what we're actually going to cover next week. But I do want you to have a conceptual understanding of inferential statistics before we get to those actual statistical tests. Let's talk more about the connection between inferential statistics and hypothesis testing. When we conduct inferential statistics, we are testing our hypotheses. Okay, so often we use these terms interchangeably, but inferential statistics is a form of hypothesis testing. And whenever we use inferential statistics, we're actually testing two hypotheses. We're pitting these against each other. And we're going to end up accepting one or the other hypothesis. The two hypotheses that we're testing are what we call a null hypothesis and an alternative hypothesis. Let's distinguish between these. A null hypothesis is, let's say we're doing a bivariate test of correlation. A null hypothesis is when there is no relationship between our two variables of interest in the population. Okay? So for example, if we think about the previous example we were just looking at, the null hypothesis would be that there is no relationship between generation and attitude toward legalization of marijuana in our population. All right? On the other hand, our alternative hypothesis is when there is a relationship between our two variables of interest in the population. For example, perhaps there is a significant generational difference in attitude toward legalization of marijuana in the population. Basically, with inferential statistics, bringing it back to that probability that we were talking about before. Inferential statistics is a way of testing the probability that our null hypothesis is true, given our results. Going back to the M&M's example, our null hypothesis perhaps was that there is a 25% chance of drawing a blue M&M each time. That's our null hypothesis. And in drawing our sample of M&Ms, we are testing the probability that our null hypothesis is true. Okay? The M&M's example is different from testing relationships between variables. But conceptually, we're talking about the same thing, right? A test of our null hypothesis and whether or not it holds true. There is a set order or a set number of stages for engaging in hypothesis testing. Okay, so we'll go over this. This is coming from the book. But when you do hypothesis testing or inferential statistics, here are the 4 stages that you're going to engage in. The first is to set up a null hypothesis. So as we mentioned in the previous slide, a null hypothesis is stating that there is no relationship or correlation between examined variables in the population. Okay? That is our null hypothesis. Then we're going to, step 2, is deciding on an acceptable level of what we call statistical significance. We have not gotten to this yet. We're going to get to it in the next few slides after this one, okay? So just hold on to that idea that this is a stage of hypothesis testing. We'll get back to it. Then we're going to use a statistical test in order to test our hypotheses, right? This is something we're going to talk about next week, those specific statistical tests that we might use in inferential statistics. Okay? And then finally, we're going to assess our null hypothesis. If we get to that acceptable level of statistical significance, we are going to reject our null hypothesis. For example, going back to the example of generational differences in marijuana attitudes, we might infer, if that acceptable level is attained, that there are significant generational differences in marijuana attitudes in the population. Okay, that would be rejecting our null hypothesis, because we are rejecting that there is no relationship between generation and marijuana attitudes. I know that there's a double negative here, and that makes this hypothesis testing language a little bit confusing. But with a double negative, we then infer a positive. If the acceptable level of statistical significance is not attained, then we fail to reject the null hypothesis, which basically is a triple negative now. So in the example from before, we might infer that there are no generational differences in marijuana attitudes in the population. So we're failing to reject our null hypothesis. This is still pretty conceptual and talking about the language of hypothesis testing. Hold on to this because we're going to continue to do examples to clarify this language. Let's talk about statistical significance in relation to hypothesis testing and inferential statistics. You have probably heard the phrase before. You've read, when you were doing your lit reviews, you probably saw somewhere in the studies that you read that phrase statistically significant difference. We see this in a lot of areas of research. What does this actually mean? Well, it turns out statistical significance is a key component of hypothesis testing. And I'm getting a little ahead of myself here, but remember that when we did the M&M's example, we calculated that probability. We could call that a probability value. That is the value that we are going to use to gauge statistical significance. And we use these tests of statistical significance to infer whether or not we should reject our null hypothesis. Okay? Some of you have probably heard of, and if you did the readings, you should have read about p-values. When we conduct inferential statistics, we get a number that is called a p-value, and this is the value that we use to decide whether we're going to reject our null hypothesis. Okay? We will do the actual statistical test. We'll talk about the actual statistical test that we do in order to get that p-value next week. But I do want you to know what a p-value is and what it tells us. So what is this p-value? P-value is short for probability value, right? That's why we're talking about probabilities this week. And specifically, the p-value tells us the probability that we would get our results, the results that we get in our study, if the null hypothesis is true. In other words, it's telling us the probability that there is no relationship between the variables we are testing in the population. Let's go back to that M&Ms example. There we were testing the probability that we would draw 10 M&Ms in a row that are blue if our null hypothesis is true, right? 10 blue M&Ms in a row if our null hypothesis is true. And our null hypothesis is that there's a 25% chance of drawing a blue M&M each time. So in this case, our probability value is very low. It's very unlikely that we would draw 10 blue M&Ms in a row if our null hypothesis was actually true. Okay? Importantly, our p-values are going to range from 0 to 1 because they're probabilities, and probabilities range from 0 to 1. A smaller p-value means that there is a lower probability that we would get a result if the null hypothesis is true. And then we can flip that, as we commonly do in our social science research and inferential statistics. We can flip that to say that there is a higher probability that there's a significant relationship between the variables in our population. Okay? Let's talk about what p-values can and cannot tell us. And also I'm going to give you a rule of thumb for determining whether our p-value means we have statistically significant relationships. So as I just said, we do have a rule of thumb for whether or not our p-value tells us we should reject or fail to reject our null hypothesis. Okay? Here's the rule of thumb. If we have a p-value that is less than 0.05, the rule of thumb is to reject our null hypothesis. If our p-value is greater than 0.05, we fail to reject the null hypothesis. It is important to note here that this threshold of 0.05 is completely arbitrary. Okay? I actually don't know the complete history of how we got to 0.05 as the threshold for our p-value, but it is an arbitrary threshold. And this can be and has been considered to be problematic in a lot of research, a lot of discussion of the kinds of methods that we use to determine whether we have statistically significant results. It's arbitrary. However, this threshold of 0.05 continues to be widely used as the standard threshold in quantitative research. Okay, so we continue to see it used regularly in social science research, and you probably have come across some studies that do talk about and report p-values, okay, and use this same exact threshold. Finally, I want to discuss what the p-value does tell us and also what it does not tell us. Okay, so the p-value doesn't tell us everything there is to know about our hypothesis and about our research, right? The p-value does tell us the probability that we would get our results if there was actually no correlation between our variables of interest in the population. So recall that what we're talking about here is our null hypothesis. We are testing the probability that we would get our results if the null hypothesis were true in our population. That's what the p-value does tell us. Here's what the p-value does not tell us. First, it's not telling us anything about the magnitude of a correlation or relationship between variables in our population. In order to get a sense of the magnitude, we might look at a contingency table, for example, to look at group differences in using the example of generation and attitudes toward marijuana legalization. We might look at that contingency table to see the magnitude of difference across generations in that relationship. The p-value also does not tell us whether our results are sociologically meaningful. So we might get a statistically significant p-value, but the magnitude of difference across groups, let's say we're still looking at generations and marijuana legalization attitudes, maybe the actual magnitude of difference is very small. It's a matter of maybe a couple percentage points from generation to generation. And with that kind of small magnitude of difference across generation, we could probably argue that this isn't really sociologically meaningful. It's not really meaningful for our research. We do see this happen sometimes with p-values, especially if you have really big sample sizes, can drive your p-value down. We won't talk about why this is the case, but it can drive your p-value down even if you see very, very teeny tiny changes across groups, or very, very weak magnitude of correlation. So we don't know, based on the p-value, if we have actual meaningful results. The p-value also doesn't tell us anything about the direction of a correlation or relationship. It's a probability. It doesn't tell us about the direction of the associations. And finally, the p-value does not tell us anything about the representativeness of our sample. In other words, we could have a biased sample if we don't use a probability sampling method that leads to biased results. And we can't tell whether the results we're getting are the case because we have a real relationship, a real correlation in the population, or whether we just didn't really collect our sample right. The p-value can't tell us the difference between these. Okay, so if you have a biased sample, you might end up getting statistically significant results that don't really reflect the population. So I have been talking a lot in this PowerPoint module and haven't yet given you a chance to pause and apply some of these things. So that's what we're going to do right now. Here is your content question to answer on Inquire. I want you to imagine that you are conducting a study to test the association between religious attendance and mental health among college students. First, what is your null hypothesis, and what is your alternative hypothesis in this case? Let's say you make a contingency table and then you run a test for statistical significance. We haven't talked about what these exact tests are yet. And you get a p-value of 0.07. How are you going to interpret this p-value? Okay, so you can pause the module here and answer this content question on Inquire. And finally, here is your closing question. Here's what I want you to answer on Inquire for your closing question. What is one thing that you learned from this module? What is one term or concept that remains unclear to you after completing this module? And I will note that these are difficult concepts to grasp, and that learning this online through a PowerPoint module alone would make this more difficult. So don't panic if you're lost on some of these concepts. We're going to practice this more in class, okay? So pause here, answer this closing question, and then come back for the final slide. All right, that concludes our PowerPoint module for this week. Here's a list of things that are coming up soon. First, we have no class this Wednesday. We are all going to be meeting on Zoom this Friday. Okay, so we're not going to have an in-class meeting, but we are all going to be meeting on Zoom this Friday. You don't have any assignments due this Friday. You do have some readings for next week. There are 3 readings, and these are introducing the specific types of statistical tests that we use in inferential statistics. Okay? Some of these you might have heard of, like the chi-square test and the t-test. You also don't have any assignments due next Friday. Okay? So this is what to look forward to in the coming week. I will see you all in class this Friday.